Well, good afternoon, everybody. Um, okay, good afternoon, everybody. Welcome to Residents Present. Today we have a very special Residents Present. Frank Bachner is going to give the talk, and it's about how our lives have been altered since a major discovery that was made in the 1940s. So let me just, not that he needs any introduction, let me just still introduce Frank to you. So Frank was born in Brookline. I have to always remember these places. They're foreign to me. But anyway, and then he graduated from Newton High School in 1957. And then he went to MIT for his bachelor's and his PhD, which he did in material sciences, and graduated with his PhD in 1966. He met Jane while he was a graduate student, and she was a student at Wellesley, and they also got married in 1966. So it was clearly a very important year for them. Then he was commissioned as a second lieutenant in the Army through the ROTC, and he went on active duty also in 66, 2 years at the Henry Diamond Laboratories in Washington, D.C. After discharge from the Army in 68, he joined the MIT Lincoln Laboratory, where he began a career focused on electronic materials and advanced semiconductor packaging. As a group leader at the Lincoln Laboratory, he was responsible for research programs in silicon device technology, thin films, and semiconductor packaging. He's promised me he's not going to go into any detail about any of that. This is all going to be very understandable. Anyway, when he then left Lincoln Laboratory to work in private industry and spent several years working in the microelectronics industry, both in Boston and then in San Diego. In the final years of his career, he spent as a consultant working with companies on marketing and strategic planning in this field. Anyway, Frank, we're looking forward to your talk.
Thank you. One minor correction, it was the Harry Diamond Laboratories, not the Henry Diamond Laboratories, with due respect to Mr. Diamond. To begin, I'd like to ask a question, and I'm going to ask Bruce not to look up the answer on his phone. How many transistors do you think were manufactured in 2022? Just take a guess. 1 trillion. Do I have another answer? Okay, 1 trillion. All right, we'll come back to that. And I want to say I'm really not that much of a technical person. I spent most of my career as a manager or in marketing, strategic planning, and market analysis. So I'm not going to talk about how transistors work, because I don't really know, or how they were built, which I knew more about. But I want to talk about the incredible magnitudes of change that have taken place in this industry and how much transistors basically are a part of everything we do, touch, feel, or think these days. And there's lots of stuff in the media about this technology. There was an article in last week's, not yesterday's, but a week ago, Sunday, New York Times Magazine, called Silicon Blockade, about how we're not letting our computer chips go to China. And there was, and a lot of that touched on many of the things I want to say today. Anyway, so just begin with this slide, which I found on the internet, which gives some sense of how things have changed. In 1966, there are a couple of people here from Draper Laboratories who know this better than I do, but Draper Labs built the Apollo 2 computer, which was used to put a man on the moon, a person on the moon, I should say. And then about 20 years later, there was a Cray computer, and then a few years ago, the iPhone 12. And the word flops is going to come up again. Flops is not the plural of flop, but it is in fact an acronym, which means floating point operations per second. And what that actually means is not important, but it is a metric for measuring the performance of a computer. So in 1966, the Apollo 2 computer, which was capable of putting a person on the moon, its power was 12,250 flops, floating point operations per second. 20 years later, the Cray supercomputer was up to 1.9 billion floating point operations per second, which was 155,000 times more powerful. And then, I'm not sure when the iPhone 12 appeared, in the late teens of this century, was up to 11 trillion. So this huge increase in performance was enabled by transistor technology. Okay, so what is a transistor? A transistor is a three-terminal device made on a semiconductor that can either amplify or switch. Amplify is fairly obvious for like a hearing aid or a radio. And as a switch, it can be on or off, 0 or 1. So binary logic, 0 or 1. And that is, as you can imagine, extremely important. The transistor was invented in 1947 at AT&T Bell Laboratories. And there have been many subsequent versions over the next few years. I'll show pictures of a couple of them. It's not really important. But the question may come into your mind, what is a semiconductor? And the simple answer is a semiconductor is a material whose electrical conductivity is in between electrical conductors, metals like copper or silver, and insulators like glass or ceramic. But the word semiconductor has come to encapsulate the whole industry. Goodness. Okay. Are we back? Okay. Okay. The whole industry. So when they talk about the semiconductor industry, and they don't really talk about semiconductor materials, they're talking about all the chips and everything that have been made. And the one thing I would like to stress is that the invention of the transistor in 1947 is considered the most important invention of modern times. And you don't really think about that, but the transistor is the most important invention of modern times. Okay, and this is the picture of the transistor that was first invented. Oh, I failed to mention examples of semiconductors. Silicon is the one whose name you know, germanium. Then there are compound semiconductors like gallium arsenide, which you might have heard of. But this was the transistor that was built by Bardeen and Bratton in 1947 at Bell Labs. And it's sort of a geeky looking thing. And then a few years later, and this is important, the bipolar planar transistor was invented, which now is flat, and that's important. And then I'm going to show one more, and then I'll just go over. And this is called a MOSFET, a metal oxide semiconductor field effect transistor, and you don't have to know what that is, but I wanted to show a picture. So if you had gone into Radio Shack back in the 50s and said, could I have some transistors, please? This is what you would have gotten. And these little top-hatted looking things are called TO cans. And I can't remember what TO stood for, but that's what they were. And so those are transistors. And they cost $8 to $10 a piece. And that's an important number to remember. So they were fairly expensive. Okay. The very first commercial product to use transistors was this hearing aid from Sonotone. It was introduced in 1952. It cost $229.50. It used one germanium transistor and two vacuum tubes. You can see the vacuum tube sort of right in the middle. I don't know where the transistor is. And the reason that there weren't probably more commercial products is because although transistors were small and light, very light, compared to vacuum tubes, they were much more expensive than vacuum tubes. And therefore, their use was pretty much limited to things that were very small and portable, like hearing aids or radios, which I'll show in a minute. And most of the effort and support for transistor technology was by the military and for the military, in the United States anyway. So then in 1954, the first radio using transistors was introduced, the Regency TR1, which was a joint venture between Regency and Texas Instrument. And it used 4 transistors built by Texas Instrument. And it sold 100,000 units, as I said. And most important, it introduced the word transistor into the lexicon, because now your kid, or at the time, I guess it was us, went out and bought a transistor because we needed to have it. And there was even a song, and I thought I would play it, but I decided not to, called Transistor Sister by Freddie Cannon. You all remember Transistor Sister. So now the word is in the lexicon, and actually I looked it up in the dictionary, and the first definition is a 3-terminal device, blah, blah. The second definition of transistor is a radio. So there you go. Meanwhile, in Japan, where there was no military activity, this was post-war, where the Japanese were, very anti-military. A company called Tokyo Communications Company was building germanium clocks and hearing aids, and then they built a radio called the TR-62, changed their name to Sony, introduced it $29.95 in 1955 in the United States, and soon just totally dominated the market in this country. Okay, now jump forward to 1959, and this is a picture of the IBM 7090. This was IBM's first transistorized computer. It used 50,000 individual transistors, and it was based on the IBM 709. And I like the fact that the project to build this was called the IBM 709T. T as in transistor. But when they actually introduced it, they just changed 709T to 7090. So a little bit of trivia. And it was 6 times faster than the vacuum tube predecessor, the 709. Okay, so now we're in 1959. Transistors are not really that big a deal. Again, mostly military. But then something happened. And the monolithic integrated circuit was invented. And a monolithic integrated circuit is a circuit that has several transistors and other components built in a single flat piece of semiconductor, almost always silicon today. Doesn't have to be. It was invented in 1959 jointly, or not jointly, but at a guy named Robert Noyce at Fairchild Semiconductor, and also at Texas Instruments, somebody named Jack Kilby. And they apparently had a big patent fight that lasted for years. It was never resolved, and everything got cross-licensed, so everybody was happy. And the first commercial IC appeared in 1964, and it was by General Microelectronics, and it had 120 transistors on a single little piece of silicon. So that's important, 120 transistors. And now we come to Moore's Law. You've all heard of Moore's Law? Everybody heard of Moore's Law? No? You haven't heard of Moore's Law. In 1965, Gordon Moore, who had been come from Fairchild Semiconductor and was the founder of Intel, and he died this year. He died in, I think, of March of this year. He made a prediction, an observation, actually. He said, the number of transistors on an integrated circuit chip seems to be doubling every 2 years. And I think that is going to continue for 10 more years. And then sort of digressing, that prediction, which became known as Moore's Law, became the driving force, the holy grail of the entire semiconductor industry. And tens, maybe hundreds of billions of dollars were spent developing the technology to allow the industry to double the number of transistors on a chip every 2 years or better. So there were 120 transistors on a chip in 1964. So how many transistors on a chip in 2023 according to Moore's Law? Well, that would be a doubling. That was 58, 59 years ago, so that would be a doubling every 29 years, okay? So, Siri, what is 2 to the 29th power? Let's see. 536,870,912. So, Siri, how much is 536,870,912 times 120? We're taking Siri as, that's 64 billion. Okay. So, according to Moore's Law, there should be 64 billion transistors on a chip in 2023. Well, that seems like an awful lot to me. Does it seem like a lot to you? Yeah, that's sort of ridiculous. So let's see what actually happened. So here's a list of, these are just a selection of chips that I chose, and I cherry picked the bottom one, which is the Apple M2, and oh my gosh, it's 67 billion. Well, Moore was off by 3 billion, but I think we can forgive him for that. So in fact, Moore's Law has held. And there are chips on the market that are more than 67 billion and lots that are smaller. But a typical chip today in your phone, in your computer, has tens of billions of transistors on it, which is extraordinary to think about. And you can look and see how that has increased with time. And some of them, do you remember the Pentium? Did you all have Pentium computers? Your Dell computer, and you looked inside, and the Pentium 4 had 112 million transistors. And then coming down to, if you have a current Apple computer, an M2 has, well, that's the M2 Max, and M1 has 16 billion transistors. And I want to call your attention to the process node. Now, that doesn't mean anything to any of you probably, but, and the unit is nanometers. Okay, a nanometer is a billionth of a meter. And so what's a billionth of a meter? Well, a human hair is about 50,000 nanometers. A red blood cell, little thing, is about 7,500 nanometers. A virus, little virus, COVID, that little thing you see a picture of every time you go anywhere with a little thing sticking out, that's about 20 to 40 nanometers. And the diameter of an atom is about 1/10 of a nanometer. So under those process nodes, that is roughly, approximately the minimum dimension of the transistor that is being built. And you can see over years, it starts with 10,000 nanometers, which is about 10 micrometers, also called microns. And over the years, we're now to the point where they're manufacturing transistors with dimensions in the order of 5 nanometers. Okay, so now we come to the answer to the question, how many transistors were made? Well, somebody guessed 1 trillion. Well, the answer is actually 2 billion trillion, which is a number of so large that it's hard to get your mind around. So I'll give you some help in that. That's 63 trillion transistors manufactured every second of the year. 63 trillion transistors every second. Or, if you prefer, 250 billion transistors for each and every person on the planet. And if I can tell you, if you think that isn't true, how you have 250 billion transistors that are governing many aspects of your life, everyday living. I also did some silly calculations. That's 4 transistors for every gallon of water in all the world's oceans. And it's 100,000 transistors for every ant on the earth. So I'm not sure what an ant would do with 100,000 transistors, although we seems to do very well with our 250 billion. Okay, so how does that get made? How can you make 2 billion trillion of anything? Well, obviously not one at a time. And in fact, these integrated circuits, which contain these billions of transistors, are made on silicon wafers and in the state-of-the-art fabrication facility. And silicon fabrication facilities are called fabs. And I don't know whether they were deliberately coined that term because they're so fabulous or whether it's just a shorthand. But in the state-of-the-art silicon fab, the wafers are either 200 millimeters, which is 8 inches, or 300 millimeters, which is 12 inches. And on each wafer, there are many chips. And then you can see in the right-hand picture, sort of showing all the little chips that make up the wafer. So on a 300 millimeter wafer, you might have as several hundred chips. Each chip has billions of transistors, which means that on a single wafer, the number of transistors manufactured runs in the trillions. And the company many of you have heard of, TSMC in Taiwan, the Taiwan Semiconductor Manufacturing Company, they make 15,000 wafers a month. Each one has trillions of transistors. So you can see how you could get to 2 billion trillion transistors, even though the number just seems like beyond comprehension. Okay. And then I found these pictures that are sort of like something you might see hanging in the Louvre. The picture on the left is an M1 chip, which has 16 billion transistors, and on the right, an M2 transistor, which has 20 billion transistors on it. So can you see them? You can see the individual ones, right? You count them. 1, 2, 3, 4. Okay. So, and each wafer has several hundred chips. So I did a rough calculation so that an M1 wafer might have 7.2 trillion transistors per wafer. An M2 wafer, maybe 8 trillion transistors per wafer. So there are a lot of transistors being made. Okay, so where do they all go? I mean, that's sort of the whole point of the talk. Well, I tried to make a list. And is there any, I'm sure there's something I left out, but when you go back to your apartment, you're going to take your card where there's an integrated circuit chip embedded in your card with lots and lots of transistors, and you're going to put it up against the door, which has lots of transistors, let yourself in, and then you've got the thermostat set so that it won't be hot and humid, and that's got transistors. And you take the remote that has transistors and you turn on the TV that has transistors, and then you check your iPad that has transistors, and you check your email from the internet, from the Wi-Fi that has transistors, and it's everywhere. But then you decide, well, I have had enough of that. I'm going to get away from transistors. So you get in your car which has billions of transistors. I mean, and you in the garage, and you approach the garage door, and the sensor, which has transistors, opens the garage door for you. And then you get to the light at the end of Great Meadow Road, and the traffic light, which has transistors, turns green because it knows you're there. And then you go to Whole Foods, and you tap your credit card that has transistors on the reader, which has transistors. So I think I'm belaboring the point, but they're everywhere. Printers, security systems, remote control, everything. So the world is full of transistors. But I want to talk about cost. I hadn't mentioned cost. The first transistors in the 50s, as I said, they were $8 to $10 each. And this is integrated circuit-based memory. And again, I have terms here that I need to define. I put the top one in red because obviously that is not an integrated circuit because they hadn't been invented yet. But a byte of memory is 8 bits, and a bit is a single 0 or 1. So memory is, when you buy your little memory stick, it says 16 gigabytes or 32 gigabytes. And I'll talk about that in a minute. And so back in 1957, you couldn't get a megabyte of transistor memory, but if you could, it would have cost $411 million. It's a lot of money for a megabyte of memory. And the 1 byte of transistorized memory cost $392. By 1974, that cost of that 1 byte of memory was down to $300,000. And then as time progressed, we get to today where 67 billion bytes cost $97, which comes out to be 0.15 cents per megabyte. So the cost of memory from 1974 to 2023 has gone from $300,000 a megabyte to 0.15 cents. And I think I calculated that I can't remember. It's a big drop. I can't do the orders of magnitude. I thought I had written it down. All right. So now let's talk about computers and how it's impacted computers. The very first electronic computer, which was not made with transistors, was the ENIAC. And a story that I heard. The ENIAC was built for the United States Army to do ballistic calculations, firing tables for artillery. And IBM chose not to bid on it because the head of IBM was reputed to say, perhaps apocryphally, but to say, the world will never need more than 5 of these, never. So they didn't bid. And then somebody else, I can't remember who, won the bid, installed the computer, and sometime later the IBM salesman was visiting the facility and heard that the computer was being used not only to do ballistic calculations, but was being used to do payroll. And when he communicated that to IBM, they realized they had made a mistake. And they obviously got into the computer business. And you can see how the performance of computers and the number of transistors, I couldn't get the number of transistors for the Cray 1 computer, but the performance just increased by orders of magnitude over time until in 2018, the IBM Summit, which is their supercomputer, had 74,000 trillion transistors and 200 petaflops, and a peta is a quadrillion. So, but I think the thing that's most impressive is that an Apple PC has 2.6 trillion flops in capability compared to the original IBM computer, which had 100,000 flops. So a computer from 1959 compared to an Apple computer that you have on your desktop that costs $500 has 2.6 trillion flops, or a billion times faster. It's just extraordinary. So, the iPhone, a supercomputer in your pocket. Every kid has a supercomputer in their pocket. It's sort of the scourge of the classroom. I volunteered in a school, and the teacher spent half his time saying, please put that away. And then he brought in a shoe bag, the shoe bags you hang in your closet for the kids to put their phones in when they came in the beginning of class, and that didn't work. So we got little locked cabinets where they could put them in with the key, and that didn't work. And they had another effect. The kids were doing exercise, doing calculations, I think having to do with the force of gravity. And I went up to one of the really bright kids in the class to see how she was doing. And she had gotten the problem completely right, but she just had one last calculation. She had to divide by 10. And I said, oh, great. You just have to divide by 10. She said, I'll get my calculator. I said, you don't need your calculator to divide by 10. And she said, yeah, I do. And she said, I'm not very good at arithmetic. This was a really bright kid. So I said, well, iPhones, I guess, are not all good. So let's look at, I don't know if you can read that. This is how the iPhone has progressed. So that in flops, so that the current on iPhone 14 Pro has, 1.6 teraflops, and just enormous computing power. And this, the things that this enables, you can take these magnificent pictures with an iPhone, which has like a $2 cheap plastic lens in it, but you can still take these magnificent pictures. You can ask Michael. And it's because of all the computing power that manipulates the image. And you can do photo editing after the fact and then of course you browse the internet, and you can even call your grandkids on your phone if you want to, although they don't want you to call because they want you to text them or use Instagram or something. And you can ask Siri, and Siri can answer all your questions. And how many transistors? So the iPhone 14 has 16 billion transistors. So how many of you realized you walked into here with 16 billion transistors in your pocket? Not to mention the ones in your watch. And if you have a pacemaker the way I do. So they're everywhere. And let's talk just sort of finally about communications. So the first commercial cellular network was established in Chicago in 1983. And the thing about it was you could only support like 10 or 12 users at a time. So Hedy Lamarr, many of you know this story, but Hedy Lamarr was an Austrian actress, born in, she was raised Catholic, had Jewish grandparents, came from Austria, and the Germans, she was frightened by the Germans, so she came to Hollywood where she became a big star. But at the same time, she really, really wanted to help the United States defeat the Germans in the war. And the US Navy wanted to control torpedoes with radio signals, but they were too easily jammed to make it work. So she, along with a co-inventor, came up with a solution to that problem, which was called frequency hopping spread spectrum. So it doesn't really matter what that is, but it was 1942 when she filed the patent, but it couldn't be implemented because the transistor had not yet been invented and the computing power didn't exist. But jump forward to cellular technology, and although there were many other developments that enabled it, but spread spectrum, frequency hopping spread spectrum was a key technology that allowed cellular telephony to support multiple users at once. So Hedy Lamarr, who we all think of as a beautiful Hollywood actress, was a key inventor in supporting our use of our telephones today. And then there's Wi-Fi, which we all use, which is 808 IEEE, the Institute of Electronic and Electrical Engineers, standard 802.11. We all know is Wi-Fi. And you can connect to the internet from anywhere. Again, I don't think we appreciate that. Jane and I were in Sydney, Australia to view an eclipse, and a stupid hotel wanted to charge $20 a night for internet. And I said, well, that's ridiculous. And Sydney loves its coffee if you've been there. And there are coffee shops, 2 or 3 coffee shops in every block, and they all have free Wi-Fi. So in the early morning, I would take my iPad and I'd go stand outside one of these coffee shops and download my email on their Wi-Fi. It's just amazing how our lives have changed due to all these tiny little transistors. And finally, Bluetooth, which connects, many of us here have hearing aids, connects hearing aids to the car, connects your phone to the car. And Wi-Fi was developed jointly by 3 companies, Intel, Ericsson, a big Swedish electronics company, and Nokia. And they were meeting, representatives from these companies were meeting, I think in Denmark, and to design this technology. And they needed a code name for it. And the guy from Intel said, well, King Harold in 958, not 1958, in 958 of the Common Era, united Scandinavia. And we're here to unite the cellular and personal computer industries. So let's code name this after King Harold, who was also known as Bluetooth because he had a rotten tooth that was blue, and he was known as Harold Bluetooth. So they called the technology, it was supposed to be temporary, Bluetooth, but by the time it came ready to go to market, they couldn't find another name that wasn't already available on the internet, so they decided to stick with Bluetooth, and we all now know Bluetooth. It's part of our lives. So that's sort of what I'm here to talk about, but I'd like to just put this in perspective. The semiconductor industry revenues for 2022 were $574 billion. I saw another number, $599 billion. Walmart's revenues for the same period were $611 billion. I'm not sure what that means, but it's something to think about. Maybe because both Walmart and the semiconductor market are so important in our lives. Okay, I'd be glad to answer any questions.
Any takers?
No questions?
No.
It's David.
Oh, hold on.
I know lots of economists worry about stuff like productivity growth and adjusting for product improvements in measuring inflation. Have any of them thought about somehow, joining forces with a bunch of electrical engineers and trying to do a more precise job of the process?
There was an old joke. I can answer that very truthfully. I have no idea. I really don't know.
So can I just ask you, do you think Moore's law will continue for the next 10 years?
The efforts that have gone into achieving that doubling every 2 years continue. I sort of read in technical magazines some of the things that are happening. They're truly investing billions of dollars, billions of dollars in developing the technology to make things smaller. They won't get much smaller than they are now, but they go to 3 dimensions on the surface of a silicon wafer, building things up in 3 dimensions. So, and for the past several years, there have been prophecies that Moore's law is going to break down, but it hasn't. And so it can't go on forever, but it's gone on for a long time.
One more question.
So with all these transistors being developed, one consequence seems to be the artificial intelligence world.
Yeah.
Do you have any prognostications or thoughts about the implications of this huge development of transistors and the future of artificial intelligence together?
Well, I would like to say that that this talk was developed by ChatGPT, but I couldn't download it onto my iPad because my iPad's operating system won't support ChatGPT. Obviously, artificial intelligence is enabled by the incredible computing power of today's computers, and that has been enabled by the vast number of transistors that are incorporated into even a computer in a cell phone, or as we saw in a supercomputer. But what's going to happen with artificial intelligence is, as people say, it's way above my pay grade. Michael, did you have a question?
Michael's think alike. Oh, wait. We do have
Oh.
one more question.
Oh, yeah, yes.
How much
Oh,
does
I
the
tried
transistor
to
cost now?
calculate that. It's like a billionth of a penny. I mean, it's really a tiny amount. Again, a megabyte of memory is 0.15 cents. And I mean, there's all different kinds of memory, but just say that's 10 transistors for a megabyte. I mean, 10 transistors for a byte. So that'd be 10 million transistors for 0.15 cents. So
Dirt cheap.
if you can do that arithmetic with all those orders of magnitude, it's pretty small, in the billionths of a dollar, billionths of a cent. Compared to in the 50s of $8. I wish my car had come down that much. It's really, the magnitudes are extraordinary. Yes.
Hold on. Why don't you guys put your hands up when I'm like all the way over here?
This is a really dumb question because I don't understand much about electronics. Are all of these gazillions of transistors the same? It's just a matter of piling more and more of things that do the same thing into one chip, or are these designed for specific tasks?
Well, they're all, the billions of transistors on a chip generally make up a function, like a microprocessor would run your computer, or there could be graphics processing chips that are used to do the imaging on the screen of your computer, or the chips that do image recognition. And so the chips have different functions. The transistors are 0 or 1. The chips have many different functions. Like the ones in your key card have the function of opening the door for you, which is pretty valuable if you need to go to the bathroom.
If there are no other questions, I'd like to thank you for a most stimulating and illuminating talk.